Well, hello and welcome to everybody joining us for the 2024 Westport Astronomical Society free online science lecture series. Thanks to everybody that came from LinkedIn, Instagram, Facebook, Mastodon. If you're over on YouTube, give it a thumbs up, like, subscribe, all that kind of stuff. And we appreciate you doing it. You can watch a lot of our past talks are archived on YouTube too by years, so you can go by and check out these older talks too. Well, we welcome for the first time to the talks tonight, Dr. Cara Battersby. And tonight we saddle up to explore the extreme center of our Milky Way galaxy. It's a chaotic region containing dense gas, stars, and a supermassive black hole. From the gas flows that fuel the Galactic Center to the strange star formation it hosts, we explore physics in this galactic Wild West. And using both numerical simulations and multi-wavelength data sets, Dr. Cara Battersby outlines some of what we know, some of what we don't, and the questions that drive us forward. So Dr. Battersby is an associate professor of physics at the University of Connecticut, specializing in observational astrophysics. And Professor Battersby studies how stars are born in our galaxy's central molecular zone, that's a CMZ, by combining large observational surveys and numerical simulations. And Professor Battersby has authored over 70 publications and given over 50 research presentations. In 2017, she founded the Milky Way Laboratory, a research group at the University of Connecticut that specializes in using our home galaxy as a laboratory for understanding star formation throughout the cosmos. Please welcome Dr. Cara Battersby. Welcome, Doctor.
Thank you so much. Thank you for the warm welcome. Very much appreciate it. Somebody read my website.
Yeah, kind of went through a little crib notes there.
No, I love it. Thank you. Um, it's an honor to be here. And honestly, looking at these amazing photos that y'all have taken and the ones that have been sent in to the group, I'm really, really impressed. Those are fabulous. I live in West Hartford and I have two young kids. So like when the aurora was happening on Friday, we were like fighting kids to go to bed. And then I was like, oh no, and we missed it. So it's really nice to be able to live vicariously through you all for a change. Um, and thank you so much for having me here today. Um, as I mentioned when we were setting up for the talk today, I'm really only talking about probably like a quarter of the kind of stuff that we're working on in my lab today. And there's a lot more. One of the exciting new things is NASA is doing a new probe mission class of telescopes. And a mission concept that I've been working on, the PRIMA. PRIMA stands for Probe Infrared Mission for Astrophysics, was selected for Phase A funding. There's two of us who were selected. So we're going to write this proposal. It would eventually be for a $1 billion mission if it's successful. So if that happens, I would love to tell you guys more about that at some point, some of the science that we'll do with that. But for right now, I kind of wanted to just share a overview of some of the questions that are driving us and what we're looking at. So I call this talk the Galactic Wild West, and I hope you appreciate this nice picture in the background here. Um, where really I'm talking about the central molecular zone of our galaxy that I think is summarized, it's well summarized as the sort of the Galactic Wild West of our own galaxy, because all of the normal rules for star formation and how we understand physics throughout our galaxy are very different here, and they're just a little bit more extreme. So in addition to the nice introduction that Dan gave me, I thought I would also just say a couple of words about myself. So um, I have this picture of me, just a kid into science. I grew up in Massachusetts, and I always was really interested in astronomy and science. And I didn't even know you could do it for a career for a really long time. Um, and the first time I did it was as an REU student. I worked at the MIT Haystack Observatory, went to undergrad at UMass Amherst, and that was me at my first conference looking very proud. Since then, I've sort of traveled all over the world and used a bunch of telescopes all over the world. Um, I'm sort of I have mixed feelings to report that professional astronomy, as many of you probably know, has really moved in the direction away from, all the telescopes that are pictured here. These are all ones that I like sat there, I touched the telescope, I worked with the telescope, I tried to that was a big part of my PhD, was making the telescopes work. And nowadays, they send me data. I just say, do this thing. Somebody does it and they send me data. And it's very efficient, but you sort of lose out on some of the magic of that. And so, again, I think that gives me even more appreciation for the work that you all are doing, looking up at the skies and knowing them better than I do at this point, and knowing, how to use and build and set up your own telescope better than a lot of professional astronomers do. So that's pretty great. I wanted to share a little bit about our astrophysics program at UConn. It's relatively new. So for those of you who have been in Connecticut for a while, if you were like, I didn't think UConn had astronomy, it didn't, and now we do. So it started about 7 years ago, the hire of a couple of new astronomy faculty, and now we have a whole army of people. So we have 5 faculty, about 20 graduate students, many more undergraduate students, 3 postdocs. This is a picture on the bottom of Jocelyn Bell Burnell even came and visited us, which is how I know we were official astronomers. Yeah, so it's quite a big program. So if any of you are interested in coming to visit us sometime, I would encourage you. We have an awesome new faculty member, Matt Guthrie, who has worked really hard to set up our campus observatory and planetarium. Nothing too fancy, but they are working now and people are using them and doing cool stuff. I also spend a lot of my time working on outreach. This is some members of the UConn STARS program, so I'd be happy to tell you about that at some point if you'd like. This is a small subset of my research group. The work that I'll be sharing today is done by many, many people, a lot of them graduate students. They're the ones who do all the hard work, make all the magic happen with the data. So I just wanted to give them credit and thank them for their contributions. Okay, I'm going to start with stars. Although, Franco, I liked your picture better. Maybe this is from the Solar Dynamics Observatory. I just downloaded it from the internet, which is actually kind of cool, though, that maybe you all know already. But if you just look at the Solar Dynamics Observatory, you can download images from the day or from the recent past. Or in this case, this is a movie of the sun for the last 48 hours up through today. So I like to keep an eye on this, see what's going on in the sun. And it always surprises me and amazes me. And I think it's a good reminder of how, so in this talk, I'm going to talk about thousands of stars, billions of stars, hundreds of billions of stars, and how there's just these numbers that are totally astronomical and really hard to imagine, but that each one of these suns is kind of a magical place that has its own really cool dynamic ecosystem and potentially planets and potentially something like people living around it. So we know our own sun. It's my favorite star. I don't know about you. Pretty convenient though. Keeps us alive, makes the days bright, helps the moon shine, all kinds of good things. But as you all know, there's a lot of stars in the sky. This is a nice photograph that just highlights seeing the Milky Way plane across the sky at night. That's the disk of the galaxy that we live in. This is our closest spiral galaxy. So we think that our galaxy, looks something like this. I could probably give a whole talk on how it doesn't look exactly like this, but both spiral galaxies. Anyone have any idea how many stars are in the Andromeda galaxy?
I'm going to go with a trillion.
Yeah, pretty close.
1.5 trillion, somewhere in there.
Yeah, I think that's about right. Yeah, so our galaxy has about 100 billion. I think Andromeda is about 3 to 5 times bigger. So I think the numbers that you gave are spot on as far as we know. It's really hard to count all the stars. You have to make a lot of assumptions. So I think we don't know exactly, but order of magnitude, that's exactly right. And that is really just becomes an almost impossible number to think of, especially when you start thinking these are not just tiny little points of light. Like when you get up close, they would have all this interesting magnetic activity and structure, and potentially, as far as we know, planets are very, very common around stars, and life may be common too, to be determined. So this is our closest spiral galaxy. We have a lot more galaxies. This is Hubble image of the Whirlpool Galaxy, the Pinwheel Galaxy, just some favorites. Now, if you want to get really large scales, I like looking at this picture of the Hubble Extreme Deep Field. This is not a normal kind of observation that you take with a big fancy telescope like Hubble. What this was is there's this tiny little rectangle in the middle there that was a part of the sky that's pretty blank from stars, has almost nothing in it that you can see in nearby images. There's the moon to scale. Obviously, it's not taken right next to the moon. That would be silly. But just to give you a scale of like how big that is on the sky. And it was actually like a director's discretionary time. Somebody chose to say, there's all these great proposals. They want to look at this object. They want to look at that object. They want to see this galaxy or that galaxy. I have a new idea. Let's look at things. Let's just find the blankest part of the sky and just stare at it for days and days and days. Cool, right? And so normally that kind of proposal, people would say like, no, you need to have goals. What are your science measurements going to be? Blah, blah, blah. But sometimes the most interesting discoveries come from these kind of serendipitous curiosity where you just explore something for exploration's sake. And so this is the image from the Hubble Extreme Deep Field. And you can probably recognize a few shapes in here. There's a couple of spiral galaxies in the foreground that are very obvious, but then there's almost countless little dots and blips and wiggles. And those are all galaxies. And of course, we're looking at galaxies that are close by, but then within that field of view, we also have galaxies that are really, really far away, pushing back towards the very early universe. And if you're a poor grad student, you might actually be asked to count these, classify them, and you would count about 15,000 galaxies. And each of these maybe has something like 100 billion stars in it. And do you remember how small that was on the scale of the sky? Now imagine every part of the sky just filled with these distant galaxies and these billions and billions of stars. And that's the universe that we live in. And I find that to be totally incredible. But in case you're not just into abstract existentialism, we mean nothing. This actually relates back to who we are too. So where we come from. So, not where babies come from. I think we all know that. Where we come from as humanity. Yes, babies come from your parents, but where did the parents come from? Where did the apes come from? Where did the earth come from? Where did the sun come from? Carl Sagan had this famous quote that if you want to create an apple pie from scratch, first you have to create the universe. And so when you really think about where we come from, you're really thinking about how the entire universe developed, expanded. Our universe happens to have galaxies and stars. If you tweak the fundamental parameters of physics just a little bit here or a little bit there, you may never form something like a star. You may never form something like a human. And we're just a product of all of the time scale of the universe has all led to us here today. All of those things that happened were necessary to happen for us to be here. And so even when you look at the periodic table of elements, I like this one because it kind of tells you a little bit about where these elements all come from. So they're colored by these 8 different labels. So we have the Big Bang, and that's pretty much just hydrogen and helium. Those came from hydrogen and helium. In kind of the orange circle, we have dying low mass stars. So lithium, carbon, nitrogen, a bunch of others. Below that is dying high mass stars. So oxygen, sodium, magnesium, neon, aluminum, silicon. And then you also have merging neutron stars, white dwarf supernova, radioactive decay, cosmic ray collisions. And then as you get higher up the periodic table, you get human-made. And now here's the same chart, but looking at elements in the human body, right? So the common elements, hydrogen, carbon, nitrogen, oxygen, so on and so forth. And then we look back and we see most of these, well, they all certainly all came from processes happening in the universe, but they also came from stars. So there was no carbon at the beginning of the universe. There was no nitrogen. There was no oxygen. All of those things came from the birth of stars, the death of stars, and then the cycle creating new stars with us here.
Can I
So I'll
ask you,
share,
how many
yes.
supernovas did it take to create the metals that are in the human body? Was that like, I'd heard like 2 to 3 at least, because the first supernovas didn't really have a lot of metals in it, and that it took more supernovas after that to really create the heavier metals that are inside of us and that are in our planet and in our solar system.
Yeah, people think that has to be at least like 3 generations of stars at a very minimum. But stars have different lifetimes. Stars are very interesting creatures. They go through so many interesting phases. They can be temperamental. But what happens to a star depends entirely on its mass. So high mass stars have really short lifetimes on the scale of the universe. And so those are the ones that go supernova. And so you could have a couple of high mass stars that live and die, live and die. And maybe you only have 3 of those in like your particular part of the cosmos where like you're getting metals mixed in. But then the low mass stars like our sun can last for 10 billion years. Some can last for even longer than that. There are some stars people think that could have been from the first generation of stars that may still be around today because those low mass ones live for a really long time. So saying like how many stars is actually a much more complicated question than something that's, it doesn't have a simple answer. I think something like 3 supernova, 3 generations of stars with like 3 supernova is definitely a good lower limit. It sort of has to be at least that much. But then there's going to be lots and lots of things happening from lower mass stars that there may have only been 1 or 2 generations of those.
Oh, thank you. Thanks for that.
Yeah. And so just coming to this expression from Carl Sagan, we are made of star stuff and we're a way for the cosmos to know itself. So again, going from the abstract existentialism of hundreds of billions of galaxies with hundreds of billions of stars scattered across the distant universe, none of which we can travel to in the other galaxies. So really, this is really the story of us. You, like your fingers, your hands, the atoms in your body, they came from stars. And so that's one of the reasons I study stars. I'm so interested in the stars, and I'm really interested in learning about how they form, because it seems a little bit magic. You have this vast cosmos with this interstellar space that seems so empty, but then slowly, gradually, the force of gravity can sort of pull some things together and ignite nuclear fusion in the inside of that and form stars. And so that's the process that I study. And like I said, I mostly study in the center of our galaxy. So I think I'm actually going to skip the next slide, and we're going to just look at the Orion Nebula. You guys all know where the Orion Nebula is? Yeah, so we have Orion the Hunter. Even I can find Orion in the night sky as like a desk job astrophysicist. And the Orion Nebula is, a beautiful sight to see with a telescope on a dark night. And here are some of the things that we can see in the Orion Nebula. It's part of a star forming region, and so we have this cold dust, these dark parts of the Orion Nebula. These are the places where actually new stars are being formed. It's the part of the cloud that's extremely cold and extremely dense. And if you want to have gravity be able to collapse something down from these massive scales of the galaxy down to the tiny scale of a star and just really push all that matter together, you need to have gas that has very little internal energy, so it doesn't resist gravity. You want to have the least internal energy possible so gravity can take over, pull down, and collapse everything really well. So if you have material that's already dense, it's easier for gravity to take over. And if it's very cold, that means less thermal energy. So it's easier for gravity to take over. And so these dark, dusty parts, it's actually where new stars are forming. Whereas, the box here is showing the trapezium cluster and Orion, which are these massive, hot blue-white stars that have already been formed. And there's ionized gas all over that. And so most parts of the galaxy where we're looking at star formation are extremely messy like this. You don't say, you're forming stars and you're not forming stars and everything's a nice, happy, spherically symmetric system. It's very chaotic and all over the place. And it usually is happening all in tandem. And then around the new forming stars, you have these things called proplyds, and these are the things that are forming protoplanetary disks around young new stars, which if you didn't know anything about, if you were just a ethereal being, you might say, oh, well, what does that matter on the scale of the universe? What is a tiny little disk around a tiny little protostar? Well, that, of course, is where the planets are forming, and that's where the people, if ever they should form, will also form. And so the general picture of star and planet formation is something like cloud of gas. It collapses under the force of gravity because its internal pressure is not too high. Angular momentum conservation causes there to be a disk of material, this protoplanetary disk around the forming star in the very center. And then once the star actually forms, it blows away most of that disk. And if there's any planets there, they will be left behind, and you'll just have this exposed star with some planets traveling around it, mostly in a disk-like orbit. Again, in real star formation, this is actually quite messy, and it's not going to be spherically symmetric, and it's not going to be a simple one cloud is collapsing down, but this is the basic physical picture. And to make it even more simple, I'm a physicist, so I love classic force diagram. You do just have like a sphere, and then you have internal force. This is all the things that cause the gas to not just, collapse instantly into a black hole, right? So like, why doesn't a cloud of gas just collapse instantly into a black hole? It's because it has internal energy. It has thermal pressure. The atoms are moving around. There's turbulence, there's magnetic fields. You have all this internal energy that keeps everything in this nice, happy pressure balance. And so that's the force that's pushing out. And then, of course, gravity is the force that's always pushing inwards. And so if the gravity is stronger than the internal pressure, then the cloud can collapse down and form a star. Okay, happy little force diagram. I also sometimes think about it as like a fight between gravity and the gas pressure, but I decided I like My Little Ponies better, and I thought this is a better analogy. So gravity is really like that friend. I don't know if you guys have one of those friends, but that friend who just always wants a hug, even when you're like, I'm good, not really a touchy-feely person. Bring it in. Give me a hug. That's gravity. Gravity wants everybody to be together and just give them one big hug. And then the gas pressure is, that resistance to just wanting to be hugged all the time. Okay. So real star and planet formation is not as simple as My Little Ponies, and it's not as simple as physics force diagrams. And here's a simulation from the StarForge collaboration that actually does a really beautiful job of, so this is a numerical simulation created inside of a computer where you start with initial conditions for a molecular cloud deep in space, and you just allow some turbulence, some internal energy for the gas, and you just let physics do its work. And you have time steps in the simulation, and you check in on it. And so in this simulation, we're going to see if any stars form and what happens. You can see that the simulation is moving forward in time, and it is also zooming around in the simulation. Okay, so I think we start to see some parts of the clouds get a little bit denser. There's some little white dots there. Those are the stars that are starting to form. And you can see that some of them actually have little jets emanating from them. This is what really happens in space, that as the protostar is accreting new material, some of it gets shot off in these jets, and you can have a bunch of these jets all happening at the same time. They can be going in different directions. And then you can see right now in this cloud, the star formation has really accelerated from just a couple of clouds to just an explosion of new stars. And so gravity is just pulling all of these things together. And you can see a couple of the stars there went supernova with those bubbles around it. Some new stars continue to form. But as those stars go supernova, and as these jets continue to flood this cloud, they basically start to have the opposite effect. So gravity was pulling everything together, but then these jets and these explosions, they start to actually push everything apart, tear everything apart, and just destroy this molecular cloud. And so you're left with just the stars there in the end, and a little bit of gas there that kind of reflects the light, makes some of these beautiful nebula that we see, but that isn't really capable of forming stars anymore because so much of it has gone away. And it has too high of internal energy, can't really make new stars. There's one of these, another little burst of star formation in this one. It's like the fireworks. So you can see some of those bubbles having been carved out in this cloud. Some people think that those explosions can actually drive new star formation on the edge of the bubbles, and that like that middle part that's been cleared out is done with star formation, but the bubbles on the edge form new ones.
This
So
is
we
a
don't get to.
great video. This is really.
Yeah, it's amazing. If you just look at Starforge, they have a bunch of videos on YouTube. This is my favorite one, but they have more. It's really an amazing simulation. They've done an amazing job. Great physics and just incorporate it in a really smart way. And of course, we can never watch this in real life with real observation. So no matter how great our telescopes are or how dedicated we are, we're never going to see this in real life because this whole process is taking millions of years. Okay. And so that's why we have these really nice numerical simulations, and then we can compare little snapshots of them with what we see. So I hope that when you're looking at nebula next time, you can sort of be like, I'm just looking at a snapshot of this massive like fireworks explosion, this beautiful display. So I've said a couple times that star formation is complicated, and you could see from the video, and you have seen from your own images, I'm sure, that the physics itself is simple. We can just draw a simple force diagram, but then all these systems are interacting with each other. Gas is continuing to accrete onto the cloud. It's continuing to accrete on individual protostars. And then if you have a jet from one, that's going to impact the protostars nearby. It's just a chaotic system. I think chaotic is the best way to describe it. So when there's chaos, it's not deterministic. This is why we run numerical simulations. So we try to create laws for star formation to understand how this process happens, and ideally to take things that we can learn from the clouds that we can see in great detail, and then compare them with things in faraway galaxies. How do we understand star formation in a galaxy halfway across the universe? We can't see individual protostars. We can't see the jets from those stars. We can't see a nebula from that. So we have to take measurements of the clouds near us and then try to apply those to the distant cosmos and try to learn about that. So one of the ways that we might do this is to try to come up with a rule for star formation. Let's start with something really simple. Let's look at the number of young stars versus the mass of the birth cloud, the like molecular cloud that the stars are forming in. Do you guys think you should have more stars if there's a more massive cloud, or fewer stars?
I would go with well, the more massive the cloud, I would think that there would be more stars.
Yeah, I would too. So something like this, right? You have more stars. If you have more stuff in the cloud, you're going to be able to form more stars with that. So some early work with that did not show this nice trend. This is what we like to call a scatter plot in physics. You did not have this trend. And so it's not as simple as just, well, how much material is in the cloud? I will tell you how many stars are going to form. That's what you'd really like to be able to do, to be able to look at a galaxy halfway across the universe and say, well, how much material is there? Here's how many stars are going to form. A simple conversion between those two. But it's not that simple because it's not just how much stuff there is, it's how dense that stuff is. Because it's not just any old gas that's going to form a star. It has to be the densest gas, the coldest gas. So the only thing that matters to how much stars are going to form is how dense that gas is. So instead of looking at the mass of the birth cloud, if we look at the mass of the cloud above a certain density, okay, now we're talking. This is a relationship. And so we know that for a rule for star formation, we know that there's a direct relationship between the amount of dense gas that you have, so dense gas versus star formation. So this has been awesome, but there is something else. So this is all these clouds here. You might recognize the name of some of these complexes. These are all regions that are extremely close to the sun. This is like what we call our solar neighborhood, just this tiny little window of our galaxy right around our sun. And you can measure these things and create this nice curve and say, okay, now I'm just going to look at a really distant galaxy and say, well, I know the mass above a certain density, so here's how many stars it's going to form. But then you're making the assumption that it doesn't depend on the environment at all. What if you're right near a supermassive black hole? What if you're here? What if you're there? Does that matter? And so here's where we come in to start looking at this question in the center of our galaxy. How does the star formation law change, if it does change, in a different environment? So here's a nice cartoon picture of our galaxy from the top down. Again, one of those things we will never have a picture of our galaxy from the top down. It's just infeasible, unless you can wait for like, probably millions of years, but yeah. Because to get above this high, yeah, you're talking tens of thousands, hundreds of thousands of years to send a probe up, take a picture, and get the data back, traveling at the speed of light. So I guess I should never say never. Seems unlikely. Anyways, this is a picture of our galaxy, a cartoon of our galaxy. Here we are at the sun. That little circle there is kind of what I call our solar neighborhood. So those are like the nearby gas clouds that we were seeing. And I like to refer to this as like, this is like the ladies of Downton Abbey sitting down to have a cup of tea. It's a very well behaved, prim and proper part of our galaxy. Whereas the center of our galaxy is like Grand Theft Auto on Wild West shootout mode. It's really all the laws are being broken. The tea has definitely been spilled in the Galactic Center. And what's nice about the center of our galaxy is that it's actually close enough where we can see individual stars being formed. We can measure their properties. We can study the physics of this process. Unlike these beautiful galaxies in this Hubble Extreme Deep Field, these galaxies that are halfway across the universe, I can see maybe, 10 pixels across the entire galaxy. I cannot look at an individual star being formed. I can't tell you the physics of what's happening there. So the Galactic Center has this nice property of being close enough that we can observe it in great detail, but it's different enough that it really allows us to test our theories for star formation. So I think I'm gonna, move right to here. So here's just a couple of galaxy centers. So in the top is just showing a handful of galaxies. These are Hubble unsharp mapped images, where you can just see that there's really different structure towards the center of the galaxies. Some galaxies, like this Hercules A, AGN, seen on the bottom left, have these really active galactic nuclei. The supermassive black holes at the center of the galaxies are incredibly active, and they launch these huge jets. We saw an image of NGC 253 earlier. NGC 253 has a starburst in its center. So there's a ton of star formation happening in the very center of that galaxy. And our galaxy is different than this. And I really want to know why. So the questions that really drive me are, is the star formation different in this different part of our galaxy? When you change the gas temperatures, the pressures, the dynamics, does that change how star formation behaves, or is it the same? I also want to know, why does Hercules A here have this massive AGN and we don't? Why does NGC 253 have this big burst of star formation at its center and we don't right now? And so I like to study the star formation in this region, but also the gas dynamics. How is the gas flowing? What is controlling how much material can get to the black hole? And what is controlling whether it's bursting in star formation or not? Okay, so let's take a look at our galaxy center. This is an optical light image where you can really see the plane of the galaxy really clearly. A big part of the plane of our galaxy in the visible is just this really dark band, and that's the part where it's extremely cold and extremely dense. That's where the new stars are forming, that we're really seeing all of that. And if you zoom in on this just like tiny little yellow rectangle in the middle, now we're going to look at the mid-infrared with the Spitzer Space Telescope. Now you can see the galactic plane again, right through the center. This is the disk of our spiral galaxy. We're embedded within the disk, and we are looking through this disk. And at the very center there, you can see in the infrared, it's really, really bright. You have these bubbles. You have maybe a big outflow coming from the top there, maybe from previous activity from AGN. And if we look at this white rectangle right in the middle and zoom way into the center of our galaxy, this is really the central molecular zone, is really what I study and what I look at. So the supermassive black hole is right about the center of this image, just to the right of that big bubble. There's sort of, you can actually see my cursor on the screen right now. Sorry about that, but it's right to the right of that big bubble, right in the center. There's sort of a white region. That's the nuclear star cluster right around the very center of our galaxy where the supermassive black hole is. So this is Spitzer data. This is looking at the mid-infrared, and actually you still see some shadows. You still see some dark dust there. This is the regions that, again, it's so cold and it's so dense, it's actually blocking the light even in the infrared. You can't see through the cloud. It's dense enough that you can't even see through it in the infrared. It's like me just putting my hand in front of my face in the camera. You can't see me because it's just blocking the light. And if we go all the way to the far infrared, really far from the visible part of the spectrum, we start to see that really, really cool gas and dust. And that is in this red image here. And if you look closely, you can see that the red, the cool gas and dust, is an exact opposite to the shadows that you saw in the previous image, okay? So we're really going to really, really long wavelengths here to look at the very cold, cold, cold gas and dust that's forming the new generation of stars. So this is probably one of my favorite images because it summarizes so much of what I work on and what I find interesting. There's a million questions to ask in this image. Why is it so asymmetric? We don't know. We have ideas. But anyways, I'd love to geek out about this if you guys want. So because there's this black hole in the center, I said that one of the key questions that I have is, currently our supermassive black hole is not active. It's not accreting material, and it's not blowing out material through these massive, powerful jets. If it were, those jets can be extremely, extremely powerful. They can completely disrupt a galaxy star formation, how it's evolving. It really just changes galaxies in a really big way. And so this central molecular zone of our galaxy is really what's controlling how much gas can get to that black hole and how much cannot. So just a really quick description. A black hole is a point in spacetime where gravity has crushed mass down to an infinite density. This is called a singularity, with a gravitational field so strong that even light cannot escape. Every galaxy, with the exception of maybe a couple of weirdos, has a supermassive black hole at its center. In our case, that's about a 4 million solar mass black hole at its center. Where did they come from? How did they get to be so big? Were they there when the universe began? Were they from a first generation of stars? Tons of open questions that we're really interested in learning how these black holes grow and where they came from. Here was some early evidence for the black hole at the center of our galaxy. This is a time-lapse image where you can see these little rainbow dots are actually individual stars that people spent, decades tracking their orbits. And you can see the stars kind of loop around this empty spot in the middle of the map that's blocked with a star. That is the black hole. And you can do physics and look at those orbits and say, what is the mass of something that causes those orbits? How does it swing around like that? And it really just comes down to, so that was some of the first evidence of the supermassive black hole at the center. As a physicist, I'm totally convinced it's obviously black hole, but you have to ask all the questions. Well, what else could it be? Or how did this happen? Or why can't we see it? Da 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 da. We actually have a real picture of the supermassive black hole in our Galactic Center. This is from the Event Horizon Telescope team. This is the image of Sagittarius A star. We're seeing like a photon ring around the black hole, which is where light just barely can escape from the black hole. So it's just right outside the event horizon of the black hole. And you have all these weird general relativistic effects where the photons are basically just like orbiting around the black hole. And you can actually see those photons in this interesting way.
That's also called an accretion disk, right? Same thing.
This one is actually not an accretion disk. That's a great question. So some supermassive black holes do have accretion disks, and those are like where material is actually flowing directly onto the black hole. Our black hole, we don't think is accreting any material right now. It doesn't have an accretion disk right now. This is literally just photons, particles of light orbiting around the black hole, and then getting bent and curved in funny ways due to gravitational lensing.
And then if we did have an accretion disk, that's when you would see the beams coming out of the top and the bottom of the black
Yes.
hole and shooting
Yep.
off and
Yeah, and I
shooting
could show,
north and
and then
south.
I'd be able to show you a picture of the accretion disk. It would light up in X-rays probably, like other accretion disks do light up in X-rays or gamma rays or UV. You'd be able to like actually look at the accretion disk because the accretion disk has photons, it has light. You'd be able to see it, no problem. It's because ours is not really accreting.
And that's because it's not feeding right now. It's another way of kind of putting it
Yeah.
so if it was, I mean, it certainly has in the past, right? We
Yep.
assume. And
Yes.
so it's turned on and off. What is the future of that? Will it obviously it'll turn on again? And with these stars that are zipping around it, why doesn't it gobble those up?
Yeah. I think you're asking all the right questions. Come join my research group and help me answer these. Yeah, so the stars question is easier to answer. They're not close enough to be gravitationally pulled in. They have stable circular orbits, and so they don't get gobbled up by the black hole. A black hole, even though it's scary and has a lot of gravitational potential energy, it doesn't actually do anything special gravitationally. It's just really, really massive. So, for example, if our sun turned into a black hole instantly, that had the exact same mass as our sun, so the mass doesn't change, it just becomes a black hole, what happens to the Earth?
Nothing.
Nothing. Yeah. I mean, eventually we all die because the sun powers all life on
Cold.
Earth and energy. Yeah, we definitely die eventually. But meanwhile, the Earth just keeps orbiting. The orbit would stay the same. It doesn't get sucked in, nothing gets sucked in. So similarly, the stars that are orbiting Sagittarius A star, they're in stable orbits. Whatever it was going to suck in, it was going to what would have happened before.
I've heard that it's actually very difficult to try and go into a black hole. I mean, you could figure it out. I mean, mathematically, you could do it, but with just stuff kind of zooming around the universe, it is kind of, or in the solar system or in the galaxy, I should say, it's hard to just kind of go straight in there.
Yep. Yeah, it's very complicated. Hollywood makes it look too easy.
Right. Yeah.
Yep.
Well, thanks
Good.
for reading that.
Yeah, and so I mean, just to sort of echo some of what Dan was saying, I mean, this is really a key question that I'm asking in my research group is, so this is sort of like a top-down view of what we think the center of our galaxy looks like. So the bottom picture, the bottom arrow is showing like where our sun would be. So like we'd be looking through the plane of the galaxy like this. And so we have these dust lanes, which is what driving material into the center of our galaxy. And then the central molecular zone, the CMZ, which you already looked at this nice picture of on the left here. This is the region where if new gas is going to fall into the black hole, it has to go through the central molecular zone first. So basically, like if a cloud in the central molecular zone loses some angular momentum, maybe then it travels into the black hole, maybe a star forms and blows out some jets, and the material from that jet goes into the black hole. This is what we're trying to understand. So there's a couple different telescopes that I've used. This one is from the submillimeter array, which is those little tiny dishes in the valley in this image here. This is looking at really high resolution, so using interferometry and looking at these long wavelengths so we can look at actual star formation happening. I like this time-lapse video from Jason Chu, which shows the submillimeter array operating. As you can see, the Milky Way rising at night and the telescopes sort of following the center of the Milky Way, then turning to do some kind of calibration checks and then turning back to the Milky Way. And so we did this for about 60 nights in Hawaii to do the CM Zoom survey, which I'll be talking about in a moment. And we're also using new data from the Atacama Large Millimeter Array in Chile, which is, 64, I think, telescopes. And it's just a really big, huge project. We're doing about 100 hours on that telescope as well. This work is a collaboration of many, many, many human beings, real people, only some of whom are pictured here. And I'll just sort of show just like a really quick highlight. So this is showing sort of what we had before one of these surveys, where we have this dense molecular cloud. In this little inset here, you can see that it's really, really this cold, dense gas. It's completely blocking the light behind it. And for the very first time, we could use this survey to actually look inside this cloud and really see what is happening inside the cloud. Mm-hmm. So this is one of the images from this survey, looking deep inside these clouds. And what we're seeing now is we're seeing where the new stars are being born. Now we can start to count the stars, look at the properties of the stars that are forming. Is it forming stars like we expect, or is it not forming stars like we expect? Here's another beautiful image where we just have a couple of these clouds. Red is showing our new data, and then the green and blue is showing far infrared data from Herschel and from Spitzer. With the ACES project, we're looking at spectral lines as well. So this is an HNCO map, which we could have a whole discussion about chemistry and why we're looking at HNCO, but it seems to do a really good job of tracing out where all of the dense gas is. But it also, instead of just giving us information about where things are in the plane of the sky, they show us the velocity as well. And so we can make these nice velocity cubes where we have information on the plane of the sky, but we can also look at from the Doppler shift how that gas is moving towards and away from us. And so we use this data to try to get a picture of the whole dynamics of the region, how is the gas moving, and to also learn about how the stars are forming. So to show one quick example, we can look at these three clouds here, which I call the three here in the middle of the galaxy. So these ones, they kind of look like the little pigs in this particular color scheme. There you go. If you didn't see it before, you see it now. I called them the three little pigs though, because they showed really different levels of substructure. So now there's these contours on top of it, which is showing us where the dense gas is in these clouds. And so the straw cloud on the left, even though it looks the same as the other ones in the previous image, it has almost no substructure. The Styx cloud has a modest amount of substructure, and the stone cloud on the right has the most substructure. So what we learned before is that the rule for star formation is that you have more dense gas, you're going to have more star formation. So this is the kind of study that we do, but not just doing it in, these three little pigs clouds, but we do it across the entire CMZ. And so this is some work that was done by a grad student who worked with me, H. Perry Hatchfield. So we count all the regions that are forming stars. We count the stars that are forming. We look at the density of the material. We also found really cool things like this is some of the protostellar jets in the Galactic Center, like the ones that you saw in that simulation. We can actually detect these protostellar jets in the Galactic Center. And if we now look at this plot that we had before, we had this nice relationship. The number of young stars as a function of the mass of the birth cloud above a critical density had this nice relationship. Okay, but now we're looking at a part of the galaxy where the clouds are much, much, much bigger. There is a lot more dense gas. So I've actually increased our scale bar here. So now we're looking at things that are way denser. So here's where we would expect our Milky Way center to be based on this star formation law that had been discovered. And here's where it actually is. And there's no numbers here, so you can't tell, but this is about a 10th. So it's off by a factor of 10. It's 10 times too low. It's forming many fewer stars than we expect based on the density. I mentioned there was another thing, environment, right? So this is the case where we think that the environment is maybe coming into play. So this nice star formation law that we had is now it's off by a factor of 10. That's bad even for astronomical standards. So looking at our really simple picture of gravity versus gas pressure, what we think is happening in the galactic center is that instead of having, one pink My Little Pony gravity for the gas pressure, if you have a certain density, therefore you can form a star. In the galactic center, you have much, much higher gas pressure. The gas internal pressure is about 10 times higher. And so that one little pink My Little Pony can only hug one blue My Little Pony. So it's only forming 1/10 as many stars as it should because the gas pressure is so much higher that gravity is that much harder for it to take over. So really we think that we're still developing the details, but that the amount of star formation not only depends on the dense gas, but it also depends on the environment, and particularly the gas pressure. And that's good news because we can measure that and we can correct for that and we can look at a distant galaxy and get an estimate of what its gas pressure should be. And then we can tell you how many stars it should be forming. So this is really exciting. And so one of the things that we're working on now is doing these large scale simulations. So the top one is a zoom in of the central molecular zone in this simulation. And the bottom one is a zoom out where you can see the entire bar of the galaxy, where this gas is flowing into the center of the galaxy from the outer galaxy and into the central region. You can see in some places in the simulation, some of that gas is flowing from the central molecular zone into the central region where the supermassive black hole is, and the gas is just constantly flowing. And so we're actually running a bunch of updated simulations on these to try to connect these questions of the star formation to how is the gas flowing and how much of it can actually get onto the black hole. So these are simulations from 2020, and I have a graduate student, Danny Lippman, who's running brand new simulations at much, much higher resolution, where we are going to be able to actually do a side-by-side apples to apples comparison of these really nice observational surveys that we have. What does this look like in terms of the simulation? And so we're trying to build this top-down picture of not only the star formation in the central region, but also the geometry. So how is the gas flowing inwards from the galaxy itself? And then how much of that gas flows inwards to the black hole? And in case this looks like a funny picture to you, you're like, what is this? This is a nearby galaxy that has these same kind of like dust stains, those dark spiral-like structures going into the center. Those are these dust lanes. We see them all the time in these nearby galaxies, and this is what we see And we see the same thing in the simulation. So these are the dust lanes. This is actually what's feeding material from the outer galaxy into the inner galaxy, and then some of which will make it onto the black hole. And we're trying to figure out how much. So we're trying to distinguish between these different models of the center of the galaxy and comparing, like I said, looking at these simulations on the left with these with our observations. This is an observation of another galaxy, but we're trying to do the same thing with our galaxy. All right, I've been talking for a while. Star formation across the cosmos, as many open questions as there are answers. Thank you so much for your attention, and I would love to entertain questions if you have any. Thank you.
Oh man, that was great. That was really interesting. Thank you for putting all that together. That was, I learned a lot in that one too. I thought, I've seen a lot of these presentations and this was all very new. I mean, I really appreciate you went through that. Anyway, so we do have a couple of questions. Shannon, you were getting some from Jim Tybor, but you were answering them for him.
Well, it wasn't totally related to what we're covering here, but I was just trying to tackle it from my understanding.
Yeah. Do you want to throw any of those out there? I mean, that Jim was asking. I mean, because Kesef Nair, if you have questions too, you can post them in YouTube right now.
I
Or
have a question.
oh yeah, go for it, Cal.
Yeah, so the Milky Way is thought to be a barred spiral galaxy. How does that affect your models?
Wonderful, wonderful question, and very well informed. Yeah, the bar is very important. So we think that the bar is it's not a fun place to hang out and get a drink, unfortunately. It would not be a very fun place to do that. But so the bar is, in these images you can kind of it's this thing. It's like that structure that makes the spiral arms not go all the way to the center. There's kind of that bar in the middle. And the bar is it's a stellar structure, so it's mostly stars that are there, but the stars have a lot of gravity. And so that bar rotates through the galaxy, and as it rotates through the galaxy, it basically causes perturbations at the very edges of that bar. So where the edges of that bar touch the rest of the galaxy, the gas there gets kind of thrown off balance, and some of it recovers, but a lot of that gas ends up funneling down along the bar and then flows into the central region. And so if you look at, there's something called the FANGS survey. I don't know if you guys have seen any images from the FANGS group. It stands for Physics at High Angular Resolution in Nearby Galaxies. But they have these large surveys towards nearby galaxies. And they found some interesting results that if you look at barred spiral galaxies versus spiral galaxies that have no bar, the properties in the center are extremely different. And so the bar is totally crucial. It's what drives that material inwards. It's what makes it such a chaotic region, because otherwise it would just be sort of a static structure. It would find an equilibrium and it would be steady state. What makes our galaxy interesting is that bar is constantly driving material in. So there is no steady state structure. You're just constantly having new material coming in. I'm trying to think of like a party where the door's open, people are just constantly coming in, and so that's going to shake things up one way or another. Maybe things are going to explode and people are going to have to leave the party, but it's certainly going to shake things up, and that's like what's happening in our galaxy, and it's totally driven by the fact that we have a bar.
Kesef Nair has a question here. So he says, I don't understand the orientation of Sagittarius A star. Shouldn't the black hole be facing the top of the galactic disk rather than pointing to the galactic arm that we are in?
Oh yeah, good question. So so the black hole itself, we think is so I think you're talking about the image of the photon ring, right? So the photon ring is facing us. I think this is the one you're talking about. So this image is so confusing. I'm a professional astrophysicist, and it took me a solid 2 hours of reading before I really feel like I understood what was happening in this image. So again, you're completely right. If we had a disk around the black hole that's funneling material onto the black hole, it would be in the plane of the galaxy. It would be aligned with the plane of the galaxy. And so from our vantage point, we would only ever see through that accretion disk. We would never see it from the top down. But because this is not an accretion disk, this is like literally just photons that are zooming around the black hole. It basically, like, you'll see this from any angle. And so the people who at the Event Horizon Telescope team, they've done all these simulations, and they're like, if the black hole is this angle or that angle, like, you still see this kind of photon ring because there's still a black hole in the center, and you still have basically this gravitational lensing of like the photons themselves, like they get into this ring. And I'm sorry I don't have a better explanation. I probably don't understand it even as well as I should. It's complicated.
Inception had that great view of the black hole that they used in that I think that really does sum up what you're saying, that any angle that you look at this, you're going to see the
Mhm.
same thing.
Yeah.
Essentially, the gravity wraps photons around so that you see every side from every angle.
Right.
Yeah,
Right.
that's right. And I guess I also like to think about it as like, so a black hole is defined by being a part of space-time where the escape speed, which means like how fast something has to move to escape from the gravitational energy. Like on the Earth, we have an escape speed. If I throw a baseball up in the air, it's not going to escape. It's going to come right back down. But if we were flying on a comet, I could probably throw a baseball fast enough that it would escape. So it all depends on the gravity. And a black hole is a region of space-time where the gravity is so strong that the speed of light, the fastest thing in the universe, cannot escape. And so we're just really looking at the part just outside the black hole where there are photons so particles of light that have not been trapped by the black hole, but they're just whizzing around the black hole. And so I think you said it really well, Shannon, that we're just seeing the black hole from every angle, like Dan said, like Inception. Yeah.
Yeah. Guess I wanted to add too, it's a great talk. Everybody should study physics, especially politicians that understand there is no difference between people and even animals. Everything is born out of stardust. When our lives end, we go back to the stars. So thanks for that, Kesef. That is right. Claire had a question too. Is there a reason to think the rules of star formation could vary between types of galaxies or a galaxy's relative position in the universe? So the whole galaxy is in a different environment than our galaxy.
Yeah, wonderful question. I think it probably does to some degree. And this is part of what's hard because I feel like as a scientist, um, I can't just throw up my hands and say, oh, well, it's complicated. Like, we'll never know. Like, you have to have questions that can be answered. And so I do think that we can come up with pretty good laws that will approximate how stars are formed, but it's still not going to be a deterministic process. So, like, if you just gave me a part of space and you were like, predict what's going to happen to this part of space in the next 20 million years, I don't think you could because I don't think it's deterministic. There's just too many chaotic factors that come into play. But in terms of like big picture stuff, we can definitely look at the laws for star formation in different galaxies, like you said, and even at different epochs of the universe. So, but we need to calibrate these laws using places, I think, that where you can actually see individual stars being formed. Because if you're looking at an entire galaxy, you just see a bunch of light. You can see like UV light or infrared light, but you don't know where that light came from. And that's where you get your star formation rates from, is that you assume that light means this many stars. And so you're not actually measuring the stars, you're assuming something about the stars. So this kind of fundamental star formation law, I think you need to start in our own galaxy where we can calibrate these laws, but then we can test them as you go to other galaxies, like you said, and also farther back in the early universe. So I think that there will be a lot of variation, but it really comes down to that basic physics diagram of gravity pulls in and gas pressure pushes out. So I think that with the star formation law, now that you're accounting for the density of the gas, so not just how much there is, but how dense it is, and you're also accounting for that internal gas pressure, I think that that probably will cover most things in the universe. Just how do you calibrate the gas pressure, I think will be difficult.
Aaron Diamond has a question too. He's wondering if you encounter, I imagine you do, dark matter in your work and how that affects star formation.
Yeah, great question. So I don't actually think about dark matter a lot, and that's because in the disk of our galaxy, um, the fraction of matter that is dark matter is actually a really, really small fraction. And so like these simulations that we're running, we don't even include dark matter. I don't think we include dark matter. I guess I'm not 100% sure. I'm pretty sure we don't include dark matter because it's actually a very small fraction of the mass. That probably sounds strange because you've probably heard a lot of times dark matter is a dominant component of mass in the universe. That is true. But the dark matter in our galaxy is in this massive halo surrounding the galaxy. And the dark matter is pretty smooth. And so it has a lot of mass, but it's all distributed over this really, really, really large area. And the baryonic matter, the disk of our galaxy, is tiny, thin, tiny little slice of this dark matter halo. And so when you're just looking at the center of our galaxy, the amount of dark matter that's there is really actually pretty small. But then when you look at the galaxy overall with that dark matter halo, it's by far the dominant mass component. But when you look at like an individual molecular cloud, people don't really include dark matter. I think it's a good question though. Maybe we should be including dark matter. Maybe there's some interesting physics there that we're missing. But the basic assumption is that it's a very small part of the mass. And so you don't actually need to include it in your calculations when you're in the disk of the galaxy.
That was an interesting question. One more from Claire too. Just from thinking about different shapes of galaxies, it seems intuitive that the gas flow would differ along with the shape and the shape of the dust lanes. Can we look at other galaxies well enough to try to study that like our own CMZ?
Yeah, another great question. So yeah, come join my lab. We're thinking about these things exactly right now. So one of my colleagues has a paper where they basically try to calculate the inflow of another galaxy by, looking at the kinematics and the amount of material that there is, and just tries to calculate how much mass is inflowing. And there's a good paper, and I think we could probably apply that to a lot more galaxies. So come join us and we can try.
Yeah, that's good stuff. Is there anything else from the panel tonight? Is there any other questions?
Well, I saw the description of the three little pigs regions, and I was so disappointed that there was not a big bad wolf rayet star somewhere in there.
We can
A
add
wolf
that.
rayet
That's a great
star.
idea.
But
Yeah.
Shannon was thinking about that one for a while.
that would explain why there's only 1/10 of the star formation you expect.
There you go.
Blew the rest away.
I have a
Bad, but
do we know if the other black hole that was imaged, like the one in M87, if there is an accretion disk there or no?
That's a great question. That is known, but I do not know off the top of my head. It is known. I'm sorry that I don't know, but
Okay, thank
yeah,
you.
you're welcome.
Yeah, Claire wanted to thank you too. She goes, "This has been so interesting. Thanks so much for your thoughtful answers." And I have to agree with her. This has been such a fun talk. I love your enthusiasm and just how you just kind of the presentation was so fun to kind of hear it and the
Yes.
way and the videos. Oh my goodness, some of the stuff that you pulled out there is just it explains these complicated and very difficult things to explain very easily when you can visually see it as well as that's been done.
Yeah.
Does AI is that kind of, I mean, everybody asks questions about AI now, but is that also another big part of kind of the next steps of being able to kind of figure out some of these things, to be able to study?
Yeah. I think it has to be. I mean, I think for better or worse, AI will change everything, this included. We have one AI project in our group. It's like neural network. So it's, we're not plugging into anything into ChatGPT, but there's an undergraduate student working in my group who's really bright, Brendan Dubois. He is studying the question of like, can we use simulations of our galaxy center to tell us about the top-down view of our own galaxy center? Because with a simulation, you can have snapshots from every angle, and you have we go over like 50 million years, you have like time snapshots as well. So you can basically generate hundreds of thousands of snapshots of what we think of what the Milky Way look like if we have, this is what you would see from this perspective. Here's a fake observation that you would see of the Milky Way's galactic center. And you just do this hundreds of thousands of times. And so you get this training set of hundreds of thousands of images that are just like the real images that we take. But in this case, you know what the top-down view is because it's a simulation, like you know what the top-down view is. And so you basically train the neural network to learn how to interpret, you know, this particular observational picture. What does that look like from the top-down view? It's a really interesting project. I don't know if it's gonna work, but we're trying it. So that's one thing we're doing with AI. I think astronomers probably are a little bit behind the game in general in terms of AI can do a lot now. So that's one example.
Yeah,
There's probably a lot more.
You see the depth of research at UConn, considering this is a relatively new program, or seems to be.
Yeah. And I'm just one of the 5 faculty who all work on pretty much totally different things, which is pretty cool.
Impressive.
Yeah.
Well, Franco, thank you for finding Dr. Cara Battersby. Thank you for lining that up, Franco.
Well, thank you for coming to give us such wonderful presentation. It was very engaging, and we learned so much from it. Thank you.
Yeah, truly my honor. This is a great way to spend the evening. Thank you all so much. I really appreciate it. And I'm local, so you know, like I said, I have young kids right now, so traveling out there was not ideal. But maybe in a couple of years, I can come tell you about our NASA mission concept or something.
Oh, we love that. Yeah, we definitely want to have you back. Anytime that you want to talk about something, you got an open invite. So there
Thanks,
you have
guys.
it, Dr. Cara Battersby from UConn. Thank you for everybody that joined us tonight, and we hope to see you around here next month. Now, don't forget that we are doing public nights every Wednesday from 8 until 10. We'll be open tomorrow night. If you're watching this in the future, well, there's still a public night coming up, but tomorrow it will be a good one. Just come out and see the comet if you're out early enough. So if you'd like to join us, we are planning on being open around 7 o'clock or so on Wednesday to see the comet. Other than that, thank you for everybody for joining us. Thank you for the panel. Thank you, Dr. Cara Battersby, and we'll talk to everybody soon. See you next time. Bye.
Yep.
Bye.
Thank
Thank
you.
you.